Hey everyone, how's it going? Welcome to the class. For those of you not in the class, this is a Computer Science 4300. It's a game programming course. We are on lecture number 6. So for anyone currently doing assignment 1, that will be due on Thursday at 11:59 p.m. How was everyone's weekends? Pretty good, hopefully. Today's lecture, today is the 29th of September. Man, it is hot out. It's September 29th in Newfoundland, Canada, and it's 22 degrees outside. I don't remember that ever happening before. That's crazy. With all the computer stuff in my room, I am baking here. All right, so we're on lecture number 6. Today we're going to be going over the entity manager, as well as a little review of some 2D mathematics that you'll need to know for assignment 2. As well, something new that got added since the last class. I spent some time over the weekend. So here is my YouTube playlist. I've linked this on the class website now. You can also type the !playlist command in the chat to see the public YouTube playlist. So all the lectures for the course are now public. I also went through all the lectures, and if you can see here, I made like custom thumbnails for all the videos so that it's pretty obvious like what each lecture is about. If you view my YouTube page, you can see all the lectures here. They're all coming up pretty clearly and pretty nicely. So just being able to navigate all that stuff really easily. I want to make it as clear as possible for people to be able to navigate that. Also, now that the playlists are public and the videos are public, anyone can pretty much learn this stuff, which is also something, it's a benefit of putting the lectures online, right? Is that even if you're not taking the course, you can still learn the material. And one step closer to free education, but still, I'm not releasing the assignments to the public, because if the assignments get released to the public, then the solutions will be posted in the public. And if that's the case, then I simply can't make new assignments every year. It's just so much work to make these assignments. So all the lectures are available, but just not the assignments. So let's actually just get into today's lecture. We'll be talking about entity management. So last time we talked, what did we look at last time? Let me just bring it up. Last time we looked at an introduction to ECS, so we talked about entities, components, and systems, and we showed how entities will be containers for components going into assignment number 2 and how that's going to be set up. But what we didn't talk about yet is how we're actually going to keep track of all of our entities. So entities store components, but we do need some sort of way to store those entities, right? So are we just going to put them all in a collection like a vector or a set, or how is that going to work? That is what today's lecture is mostly about. So let's get into that right now. Cool. So let's just do a little bit of review of what we talked about last time in terms of how the entity is going to be stored. So last time we showed how the entity class that we have has public shared pointer objects to all of the different components that we're going to be having in assignment 2 and going forward in the other assignments. We're also going to have a constructor on that entity. But today we're going to add some more things to the entity class, and we're also going to talk about the data management for entities. So one of the most important concepts to me personally, and should be for you going forward, is that when you're programming larger systems, the really important concept is to try, wherever possible, to separate your logic and your data. So what that means is that you want to create data structures which manage your data so your logic code doesn't have to worry about it. And what that means is, for example, if you have to store some data, say in a vector or a set or a map, and you just want to be able to say, I have this data, you don't want to be worrying about in your algorithm code how that data is actually stored and how you set that data and how you get that data. Ideally, you'd want to be able to say, hey, get this element or set this element. But whether or not the underlying data structure is a set or a vector or an array or a map or whatever, you don't want to have to worry about that in the same place where your game logic is, right? So where you're talking about doing physics or stuff like that. So what we're going to do is we're going to make an entity manager. And this entity manager is going to set up all of the entities. It's going to give us easy access to them. And so we won't have to worry about all those details about how the entities are actually being stored. So the entity manager is going to use a factory design pattern. So if anyone has not, tell me in the chat right now if you have or haven't heard of a factory design pattern before. What a factory design pattern essentially is that you have a factory class, and just like a factory in real life that makes stuff, the entity manager is going to be the factory for entities. So the entity manager is going to handle the creation of the entities, the storage of the entities, and the lifetime of all the entity objects. So we're going to have some functions on the entity manager, and these functions will be things like add entity, remove entity. Well, we won't actually have a remove entity function, but we're going to have functionality that looks like that. It's going to have the storage of the entities and the bookkeeping behind the entities. And ideally, what also should happen is that the factory should somehow also ensure that the user cannot create its own entities. So, for example, what we're going to show later is how we can ensure that the only way that we can create new entities is via the factory, right? Via the entity manager. So that way, for example, the programmer of the game can't accidentally add an entity somewhere that doesn't go inside the entity manager. One other thing that we're going to add to entities, so before we said an entity is just a container for components. That's not entirely true. There's going to be just a couple more variables that we add to an entity to give it the functionality that we want for this course. So the reason for that is that, so one of those things that we're going to add is called an entity tag, right? So it's a tag. The reason we want a tag on an entity is, for example, we might want to group entities by functionality. And so we're going to tag an entity by a string. So the entity class is going to have a string inside it, and that string is going to be the tag. And that tag's description, so the string is going to somehow describe what that entity actually is. So for example, the player might have the player entity. So for example, down here we have the Mega Man sprite. If that represents the player entity, maybe we represent it via the player tag. If we have a tile, right? So there's many tiles on this screen here. Maybe those tiles are created with a tag of tile in a string. The bullets may be given bullet, the enemies may be given enemy, etc. I just had a question in the chat. Can we have multiple tags? Of course. You can do whatever you want, right? You could have multiple tags or sub tags if you want to, but just for this course, we're just going to go with a single tag because we'll be able to do the functionality that we want based on that. So the entity manager, really, it should also have functionality for quickly getting entities of a given tag, because we might want to do something in our game, for example, which is loop over all the bullets or loop over all the tiles, right? And yes, we could say, hey, entity manager, give me all of the entities, and then check if the entity is a bullet, then do something. But that throws away a bit of performance. So in the entity manager, we're also going to have a way to store groups of entities by their tag. So, the actual entity class that we're going to be using for this course, or at least for the second assignment, looks like this. The entity class is going to store all of its public component shared pointers like we saw before. That's going to be the same. But we're also going to have 3 new variables. The first variable is an integer ID. This integer ID, whenever we create a new entity, we're just going to create it with an ID that was the previous entity plus 1. And in that way, we can do something like check to see if the entity, we can check to see equality on entities. So for example, if we're programming the Mario game and we have 2 Goombas on the map, for example, we want to be able to check to see, for example, is this Goomba the exact same entity as another Goomba? And so what we could do in order to do that efficiently is just check their ID. So for example, if we didn't have an ID, we might have to check their exact positions and their exact speeds. And in some games, maybe 2 entities could have the exact same position and the exact same speed. But in terms of collisions or something like that, we wouldn't want to, say, collide an entity with itself. And so this ID, this identifier integer here, is just going to start at 0 for the first entity and go up by 1 so that we can uniquely identify entities. Also, we're going to have a tag. We can give it some default value, say default, but whenever we create an entity, part of the constructor is going to actually give it the tag string itself. So this again would be player, tile, bullet, etc. The third one, and probably the most important one, is whether or not the entity is currently alive, right? So when we create an entity, it will be alive, or this maybe should be something like active. And what we're going to use that for, as we'll see later, is we're going to use this Boolean for the destruction of entities. So rather than directly calling something like vector.erase entity, what we'll be able to do is, if we want to destroy an entity, we can just set this variable to false, and then the entity manager will be able to delete all of the entities that are no longer active. And of course, down here, we would have getters for things like get the ID, get the tag, get whether or not it's active, but I didn't want to include those because it would no longer fit on one slide. Okay, so now that we see what the entity is going to look like, now we can talk about the entity manager itself. And again, this course is a trade-off between functionality and optimizations and usability, stuff like that. So in the entity manager, we are not going to be optimally memory efficient. We are going to trade some memory for functionality and for speed. And this, just a caveat about this whole course, right? This is not the only way that you could implement an entity manager. I'm not saying that if you implement it another way in another game, or if there's another YouTube video or another course where they talk about something like this, that my way is right and their way is wrong. I think that the way that we are going to do things is just a good balance of, like I said, the speed, the functionality, the ease of use, within the context that this is an undergraduate course with some people who may not have seen C++ before. And so you'll probably see much more complex factories or entity managers if you look at like a AAA game. But this is just for our course, this will do what we want it to be able to do, and it will do it pretty well. So what we're going to do is we're going to store all of our entities in shared pointers, and we're going to store those shared pointers in a vector. So one thing that we haven't talked about yet, one feature of C++, is this thing called typedef. So it's going to get very, very cumbersome to type out some very long container names. So for example, if I have a standard vector and that vector stores standard shared pointers to entities, then I'm not going to want to type that out every single time, right? So what I'm going to be able to do is say typedef this thing to this thing. So what that will do is we will create this keyword that whenever we call that keyword, it will actually mean this. So it's basically like a find and replace. Just had a comment in the chat, not using. So yes, we could also use, we could set this up using using, and it would have the same functionality. It's probably a little more proper, but this is just what's in the slide right now. When I release the assignment, I'll have which one we're going to do. But whether we say using or we say typedef, essentially what it both does is say that whenever we say entity vector, we mean a standard vector of shared pointers of entities. We're also going to have a second data structure. And in that data structure, we're going to store separate vectors of entity objects which are grouped by their tag. So that's how this is going to work. We're going to have a standard map, and that map is going to map strings to entity vectors. The string here is going to be the tag, and the entity vector is going to be the vector that contains the entities. So what that's going to do is we're going to store double the number of shared pointers to save on computation time in our engine. So let me just go to my Blackboard here to show you how that's going to work. So the first thing that we'll have is we will have a vector that contains all of the entities, right? So we'll have an entity here, E1, E2, E3, E4, E5, right? This will be our vector of all the entities. And now what we'll have down here is we'll have a map, and this is just my visualization of that map, okay? And in that map, we're going to have multiple vectors, and these are going to be stored by the tag. So this is tag 1, this is tag 2, and the tags might be something like tile, right? And so this vector over here will store maybe entity 6, entity 11, and entity 21. These are the IDs. But everything in this vector will have the tile tag. And so what this is going to allow us to do is say, hey, entity manager, give me all the tiles. And it will be able to just return a reference to this vector right away without you having to filter it out later. So that's what this map is going to do. All right. So in the entity manager, here's the basic structure of the first iteration of this entity manager. So up here we have our typedef of entity vec, and whether that's typedef or using, it's the same functionality. Then we're going to have our class entity manager, and our private variables within the entity manager are going to be, well, first we're going to have an entity vec, right? That's our standard vector of shared pointer of entities. And this is going to be our M entities. This is going to be all of our entities in the entity manager. That vector is going to store all the shared pointers. Then our secondary data structure is going to be the map from strings to entity vectors. And that's going to be the entity map. That's just what I just showed on the Blackboard. We're also going to have one bookkeeping integer here, or unsigned integer. And this is going to be the total amount of entities that we've so far created in the game. And I'll show you why we're going to need that later. Then the public things, we're going to have a public constructor, of course, for the entity manager, so we'll be able to create new entity managers. We're also going to have a function called add entity. And what we'll see later is what we're going to do when we add an entity. So add entity takes in a tag as the argument. This function within the entity manager is going to create a new entity. It's going to add it to the entity map and the vector of the entities, and it's going to return a pointer to that entity. And we'll see how we use that later. And the two functions which allow us to get access to the entities, well, we're going to be able to return an entity vec, and these should be const, okay? I'm going to add that in later. So we're going to return an entity vec reference called getEntities, and that will return the reference to the vector that contains everything. And then we'll also have another version of the getEntities function, which gets passed in a tag. And what that will do is it will look up that tag in the map and then return the entity vector corresponding to that tag. So that's the basic outline of the entity manager and how that's going to work. So how do we add an entity in the entity manager? Well, we have this function, which is add entity, and we're going to pass in a string tag. And of course, I don't have the qualifiers on it here because it would go off the side of the slide. And then this function, once it adds the entity, is going to return a shared pointer to the entity that we just created. So the logic flow of this function is going to be something like this. We create a new entity object first. Then we store it in the vector of all entities. So that's how we put it in the vector of every entity. Then we have to enter it into the map, right? So we have to put it in the proper vector within the map. And then we return the shared pointer pointing to that entity. So how are we going to actually do that? Well, we can do it like this. We're going to create the shared pointer to an entity as so. So we say auto e for entity equals standard make shared entity. And the entity constructor is going to take in two arguments. It's going to take in the tag. That's the type of, that's the tag of the entity. And it's also going to take in the integer ID for that entity. And so remember how we said before that we want to have each entity having a unique integer identifier? Well, all we have to do that is pass in m total entities plus plus. So what this will do is it pass in the total entities variable, and then the total entities variable gets incremented. It gets post-incremented. So if our total entities was equal to 0, then this entity would get the ID of 0, and once that is created, the variable gets pushed up to 1. So the next time we create an entity, it will have an ID of 1. Then our entities vector, we just push back that entity into the entities vector. That's pretty easy. Then we can say, hey, entity map, look up the tag look up the key tag in the map, and then push back E into that. Now, it turns out that you may say, well, what if we haven't set up the vector yet, or we haven't set up the vector within that map? Well, it turns out that C++ has this, well, some people might call it nice functionality, some people not, that if you call an entity map with a tag or a key that doesn't exist yet in the map, it will create that value in the map and call the default constructor on the value within that map. So if this tag exists within the map, it will just add it to the end of that vector. If the tag doesn't exist in the map, then it will add the vector and then add it to the vector. So that's done for us there. But of course, if you were writing like a AAA game, you'd have your own map structure, or maybe you'd be using an array with enums as indices or something like that. And then all we have to do is return E, right? Because we've added it to the vectors, and that's how we do it. Okay. And this doesn't handle every possible edge case, but we're just going to skip that for now. So I'll go look at some questions I had in the chat here. Do the entities in the top vector have no tag, or does it contain all entities with all tags? So every entity has to have a tag. In the constructor of entity, we have to give it a tag. No entity can exist without one. And so the entities vector here, this m entities vector, that contains every entity with its tags. Here, this contains multiple vectors which are indexed by the tag. So that's the difference there. Someone else says, is multiple tags per entity a future improvement that we might like? So if you want to, for the project, you can include multiple tags per entity if you find that that is necessary. But we won't need that for any of the assignments. So for the 4 assignments that we're doing in this course, we can get by just fine with a single tag, and so that's what we're going to do. But for the project, you may want that. It's up to you. Okay. So here's another reason why we want to have an entity manager. And it's that screwy things can happen in a game when you're programming it and you're messing around with vectors, okay? So when you have collections of things and you're iterating over them and you're doing things with them and adding things and subtracting things, you can run into this problem, which is called iterator invalidation. And if you've heard of this or not heard of that, just type it in the chat. I'm kind of curious to poll who's heard of iterator invalidation before. But this is a very, very important concept. And literally to the point where if it happens, your program can just crash. Or even worse, in my opinion, it can have undefined effects. So you may get duplication of things, or too many things can be deleted. And so it's almost better in a way to have your program crash than it is to have it keep running with undefined behavior, because you really don't want that to happen. Iterator invalidation is caused by modifying the contents of a collection as we are iterating through it. So as we say for this and this and this, we're modifying it. Okay, and this can happen all the time in games, and we'll show examples of that. Well, here's an example. Here's an example of adding something while we are iterating through a vector. So let's say we iterate through all of the entities to check for collisions. and we find a collision and an explosion happens. And so what we want to do is spawn an explosion entity. So what we've just done is while we're iterating through the entities vector, we create another entity and add it to that same vector. Okay. Also, that can happen when removing, and this is probably a more likely case. Let's say we iterate through the entities to check collisions, and when something collides, we want to kill it, right? And so we remove it. And so in that case, it's maybe even more dangerous where we're iterating through a vector and we remove something. So I'm going to show an example of this, like an actual programming example of this. But when can this happen? So in C++ specifically, and in other languages as well, so vector functions may cause a reallocation. So for example, when you add something to a vector using pushback or insert or in place back or something like that, the vector may get resized. And that may recreate the internal array inside the vector, and that could invalidate all pointers and iterators inside the vector, right? So the way a vector works in most programming languages is that there's an internal dynamic array structure that they have there, and you keep adding things and keeping track of the size, but at some point, the dynamic array that you've allocated gets full. So when it gets full, you have to create a new array, copy the contents of the old array into the new array, and then keep going. But when you create that new array, it's a new heap allocation, and that's going to return a new pointer. And so the iterators, which point to the beginning and the end of the array, are now completely invalidated. And so that's a really, really bad case. And the thing is, that may not happen all the time. It may, if you run your program in Windows or you run it in Linux, depending on how that compiler of C++ has implemented the vector class, then this could have undefined behavior. Could behave one way in one language, or one way in one place and one way in another place. Erasing elements may invalidate things too. So when you erase from a vector using erase or pop back, what happens is, in general, whenever you erase something, it invalidates the iterators and references that are at or after the point of erasing inside the internal array. So let's look at an example of this. So say we're in our game and we have our collisions function. Okay. So here we are in the collisions function. We've got some vector of entity of bullets. Now, in our case, we'll have a vector of shared pointer of entities, but I just typed it like this so that it fits on one line. Maybe we also have a vector of entities, which are the tiles. And then let's say, for example, we iterate over all the bullets. We iterate over all the tiles. If there's a collision between the bullet and the tile, we want to erase the bullet, right? Because as the bullet's traveling, it hits the tile, and then we want the bullet sprite to disappear. And so this is a case of that second one of erasing. And so what would happen here is, in the worst case, and usually what will happen is all of the iterators and values after B inside the bullets vector may become invalid. And that's really, really bad. So let's just have a look at that. I'm going to go over to a live programming example now. So here we are in our trusty terminal where we've done our programming before. And I've already got this set up for us so that we don't have to type all this out. But what I have is just a very simple example. I have a standard vector of integers, and I've given them some values. Okay. Now, we didn't look at this before, but there's essentially three ways that we can iterate through a vector in C++. We can say something like for int I equals 0, I less than vec.size, right? We can do the index-based approach, which was what maybe you're familiar with from other languages. We can also do what we have down here, which is called a range-based for loop, where we say for auto I in vec. Another way to do it is to directly use iterators. So I'll show you that here now. For auto it, so it is going to be the iterator object that gets returned from the vector.begin function. So you can think of iterators kind of as pointers with a little bit of logic tacked onto them. So the iterator that is the vector begin is essentially going to be a pointer to the beginning of the vector. So that's how we're going to start it up. We say we're going to create an iterator, and it's going to be pointing at the beginning of the vector. And now our termination condition is when iterator is not equal to vec.end, right? Because this for loop will keep going until this is equal to true. So if our iterator is ever equal to the end of the vector, then we want to stop. And then we say it plus plus, and what this does is the plus plus operator on the iterator object takes the iterator from one index and just moves it to the next index, okay? So if we want to get access to the elements from the iterator, well, we use the same pointer syntax that we did before. So let's say I want to change the value of, so I say if, and then I can call, for example, I dereference the iterator. If that's equal to 30, then what I want to do is say dereference the iterator again equals 77. Okay? So let's just try that. So what's going to happen now is I'm going to iterate through the array. I'm going to say if the value the iterator is pointing to is equal to 30, so that should be the third index, let's set that value equal to 77. And down here, I'm just going to print out all the values. So what we see here is where we did have 10, 20, 30, 40, 50, now we have that 77 being printed out. So that's how we would iterate through this in the array. But let's watch this. Oh, and what I can do is while I'm iterating through the vector, now, correct me if I'm wrong, but using iterators in this way, if I call vec.erase and I pass in a pointer to the iterator, then it will do the math properly for me. So this is a special case where iterator invalidation won't happen because the vector class in C++ is going to reallocate things like this. Okay. So if I do this, that should work properly. Yes. So we have deleted 30 from the vector. See how that worked? So that code is invalid. Okay. So it may invalidate it and it may not. So Strager out there in the chat knows more about C++ than I do. So this... Yeah. Okay. So it worked for this case, but let's try one of the suggestions out there where it was if this is greater than or equal to 30. And now segmentation fault. Okay. So it worked when we deleted one thing, but it didn't work when we wanted to delete multiple things. So thank you for that example. That's really great. Not only that, but let's look at some other undefined behavior. What if when it is equal to 30, so when we iterate through the array and we see 30, I want to add a value to the end, right? So vec.push back 99. So logically, what we'll see when this happens, right, is that we're going to add a value of 99 to the end of the array. So what should be printed out is 10, 20, 30, 40, 50, 99. But what we actually see was 2 99s got added. Okay? And from what I've read online, again, correct me if I'm wrong, that this is just undefined behavior, which means that on one compiler, it may do one thing, on another compiler, it may do another thing. And so we do not want to be adding to an array or a vector as we are iterating through it. Very, very, very bad. And I can create another error message here, is that let's say I vec.erase it, and then, so if I delete something and then add something, one second, I gave the worst possible example. So if I add something and then delete something, I get double free or corruption, and like, I don't even know what that error means in this context, right? Just really, really bad things happen. We do not want to be doing that. So what happened was the add, the pushback in the vector caused the vector to resize, possibly. The iterators got invalidated, and so now while I'm iterating through it, just you don't even know what's going to happen. And so you can imagine now that if this is our vector of entities, and we want to say something, for example, like if entity is dead, vec.erase entity, then we can't do that, right? We just can't do that. So that's just a live programming example of how easy it is and how many examples can cause iterator invalidation. Okay, so now we'll go back to the PowerPoint. So what we're going to do to solve iterator invalidation, well, we can't solve iterator invalidation. We can only avoid iterator invalidation. It's going to happen. It's called delayed effects. Though that's the name that I'm putting on it, is delayed effects. I'm not sure if there's a proper term for this, but that's what we're going with. So one way to avoid iterator invalidation is to delay the effects of certain actions that modify collections until it is safe to do so. So what we're going to do is we have the entity manager. And the entity manager is going to be handling all the creation and the destruction of the entities. And so this is going to be really easy because we can use the entity manager factory that we already have in order to help get us around this. So the idea that we're going to use is that we're only going to add or remove entities at the beginning of a frame when it's safe to do so. Because right at the beginning of a frame, we know that there's no code that is iterating over the entities while we're adding this thing. Okay, and I'll show exactly how we're going to do that. But first, in order to implement this, we need to have two more things added to the entity manager class. One is a vector called toAdd. So what this is going to do is whenever we want to add an entity to the entity manager, it's first going to add it to this separate array, to this separate vector of entities, which is like a buffer, okay? So whenever we call entitymanager.add, it's not immediately adding it to the vector of all the entities. It's first going to this buffer vector. The second thing we need to add is now we need to, every frame, we're going to call update on the entity manager. So we need to periodically do updates on the entity manager in order to handle this data. So before we had one way of adding the entities, and now we're going to have a slightly new way of adding the entities. So this now becomes the add entity function. So here we're going to say auto e equals standard make shared entity with the tag. So this is the same, right? But instead of immediately adding this to the vector of all entities and the map, we're just going to add it to the toAdd vector. So this is our buffer. And now we're going to return the entity. Okay? So that entity is not currently in the vector of all entities yet. What's going to happen is we're going to have an entity manager update function, which is called at the beginning of every frame by the game engine. So one slightly downside of this whole thing is that entities that we've added will not technically be available to use until the beginning of the next frame. Okay? So what that means is if I immediately create an entity and then loop over all the entities on the same frame, then that entity will not be there on that frame, but it'll be there on the next frame. And really, unless we're getting into super specific network programming code or something like that, this won't matter at all for the purposes of our course. So here's the entity manager update function. We're going to loop through every entity in the toAdd vector, and then we're going to add that entity into the vector of all the entities, and we're going to add that entity into the map indexed by its tag into that vector, okay? So it's what we did before, but instead of directly adding it to the vector of all the entities and adding it to the map, we first immediately push it to this toAdd vector, and then at the beginning of the next frame, when we call update, we go through that temporary vector and we add everything there. Actually, there's one thing that I missed here, and I'm going to add it in. Here, I need to call m2add.clear. And I know you can't see this yet, but I'm gonna bring it back up. The one thing I forgot to say here is that once we've added everything from that vector to the proper permanent homes, they're forever homes, right? We now have declare the vector of the temporary things, right? So we're not gonna add them again on the next frame. That would be bad. Okay, so that handles that. It's pretty. That handles the case of where iterator it handles the case of iterator invalidation, all these tongue twisters, where you were adding things to a vector, right? Because you're still iterating over the same vector. And even if you call add entity, the vector that you're iterating over is not going to be changed until later. And so this is going to be safe. Now let's do the opposite thing. Talk about entity death and removal. So with this system of the entity manager, we can also easily implement entity death and removal. So each entity has this m_alive Boolean variable, which just says whether or not it's still alive. And all we have to do whenever we want to delete it is set it to false. Now, there's another step, but from the point of view of the programmer, whenever we want to delete an entity, we set that to false. So, on the next frame, when the entity manager update is called, it will read that variable and remove the entity from the vector if it's false. Pretty easy. And so this is going to prevent removal iterator invalidation. Okay, so the entity manager update function now looks like this. For everything in the toAdd vector, we're going to go through and we're going to add it. And then for every entity, we say if entity is dead, remove it from the vector, and if the entity is dead, also remove it from the entity map. But be careful, because what I've done here, now you have iterator invalidation in this place, right? But C++ 11 and 17 have nice functionality that let you do this in like one line of code. So there's things like standard remove if that you can do in here. You could also say create a vector of the entities that have the tag equal to false and then remove them one by one. So the point being here is that you only now have to deal with iterator invalidation in this place in the update function. And once you solve it there, it doesn't happen anywhere else in your entire game engine. So that's really, really good. So you see that how that works? So whenever we add an entity or we destroy an entity, it's not actually added or actually removed until the next frame of the game. Perfect. So now let's talk about how we would actually use the entity manager, what it looks like to call the entity manager. So I had a question there in the chat, and it says, do all systems need to check entity alive? So that's a great question. So one thing that could possibly happen in this system is that I set an entity to dead, and then later on in the same frame, before it gets removed, I iterate over all the entities again. So in some cases, that dead entity may cause behavior that we don't want to happen, right? And so what you could do in that case, like let's say, for example, there's a bullet that died and the bullet has a collision box, or if there's a tile that got exploded and we want it to be removed. You don't necessarily have to always check alive. What you could do when you destroy an entity is remove its components. So depending on what function that you have, if you really have this like fine detailed functionality where a dead entity that is iterated over on the same frame may cause problems, you can just remove its components. And if you remove its components, then it won't have any functionality. So you do not need to check everything if it's always alive. The assumption that entities that exist are always alive is okay for our purposes. Another question, why don't you just use double buffer and fill the second buffer with the things from the first that have alive equal true? I mean, yes. So instead of deleting things, so that's a good point. So let me go back. And I think I may actually do this. I actually suggested this last year and I forgot. So the question or comment was, instead of iterating over the entities and if it's dead, remove it, what we can do is have a second array. So we set up a second blank vector. We iterate over all of our entities, and if it's alive, we put it into the new blank vector. And at the end, we set that blank vector equal to our main vector, right? So we do the opposite thing. Instead of removing the things that are dead, we clear it and re-add the things that are alive. So that's one way of doing this so that you don't run into this iterator invalidation. But standard remove if takes in a lambda function, which you can just check if the entity is alive, and it ends up being for free anyway. So it's not that big a deal. All right. So now let's look at how we would actually use the entity manager. So let's say we have an entity manager, and we just call it M entities because it's living somewhere, right, as a class variable. And now we're going to have a function which is spawn enemy. So what we would do is we just call it really, really easily. So we'd say auto e for entity equals call our entity manager dot add entity, and we give it the tag of enemy. And so what happens is the entity manager creates the object, puts it in the correct spot, and then returns a shared pointer to it. Then we can add the transforms that we need to add to this entity in order to make it work properly. So then we just immediately add, okay, let's say this is a shared pointer, so we need the arrow syntax. So the C transform component, we say standard make shared C transform the args. Maybe we want to give it a shape, right? So that's how we add an entity if we want to spawn an enemy. Now, when we want to do the collisions, let's say, for example, we want to do collisions between bullets and enemies. Then all we have to do is we can call the entity manager and say, get me all the entities that have the tag of bullet. And so for auto B, so this will be our entity, the bullet entity. So for each bullet in the bullets vector, we loop over every enemy in the enemies vector, and we say, hey, physics, if there was a collision between the bullet and the enemy, we can call b.destroy and e.destroy. So we destroy the bullet and we destroy the enemy. And inside the destroy function of the entity, we just set that Boolean equal to false. And as someone in the chat mentioned earlier, if we really care about those minor details, we could also remove the components. So we could set all the components of those entities equal to null. And then that would solve all of our problems. Okay. Now, this is a bit of a contentious point, but we're going to try this out in the course. Entity private constructor. So we can ensure, and please don't spam me with now you can't use standard make shared. I'm going to talk about that. Let's say we want to ensure beyond a shadow of a doubt that only the entity manager can create entities. So we can ensure the safe creation of entity objects by only allowing them to be created by the entity manager class. And if we really want to do this, we can make the entity constructor private and add entity manager as a friend class. And what this does in C++, if you have the constructor of a class be private, then nothing can instantiate that class unless it's a friend. So if you're in your main function and you try and create an entity by yourself, it will say, I can't do that because the constructor of entity is private. And so you can never in any of your game code create an entity because it will be a syntax error. And so that'll be pretty awesome if we can make sure that the factory has complete control over the creation and deleting of entities. Unfortunately, and this annoys me to no end that there's no way around this that I've found that's really nice, is that if you have a private constructor for a class, you can no longer use standard make shared, which is the preferred way of creating shared pointers on entities. You have to use the slightly unsafe way of doing it like this. So you can call standard shared pointer entity, and as the input to the constructor of the shared pointer of entity, you pass a new entity. Okay? So this is the way that you have to do it, and you only have to do this in one place in the entire program. And this is just because in C++ with a private constructor, you no longer can call this because the make shared doesn't allow it. Yeah, so someone in the chat said there's a workaround for it, but not for this course. This is just way easier, okay? And we're only doing this We are never, ever, ever in any other part of our program ever, ever, ever using this syntax. It will be marks off if you do it in any other place. But again, the reason we're doing it this way is because this is the syntax that allows us to create a shared pointer for a class that has a private constructor. And so I say this is not the preferred way of creating shared pointer objects, but we'll make one exception, and that exception will allow us to have this safety that makes sure that no entities will ever be created outside the Entity Manager class. And in the long run, that will save us a lot. Semanto in the chat says, would it be the same as creating a new entity separately and assigning the pointer? No, it is not. And the reason is, if we created a... So let me show what that would be, what that would look like. Okay, so over here, we can say, let me just delete all this stuff. This is from before. So what I showed was auto E equals standard shared pointer entity. And then here we have the args. Oh, sorry, no. We have new entity args. And the question was, what if we did... Oh, I got a typo. Well, this isn't going to compile anyway, because I don't have an entity class. But what if I did the following? If I said entity pointer E, or let me call that E pointer, equals new entity args, okay? And then down here, I just add E, or E pointer. Right? You'd think that that would be the same thing, but what happens now is that we don't know what people are going to do with this pointer, right? The whole point of smart pointers is that they own the pointer and that nobody has access to create or delete that pointer outside of the smart pointer. And so here, maybe down here, someone does something stupid with E pointer. It tries to do something down here, or even worse, if it calls delete E pointer, and someone else is trying to use the shared pointer. And so we never, ever, ever want to do this. The only time we want to use this way that we should never use in the first place is if we, into the constructor, pass the new entity args. And the reason for that is that there's no external variable for people to play around with to be able to modify or delete or free that pointer. Okay? So make sure that you're doing it in this way, if you have to do it this way, which we're only doing in one spot in the assignment. So any more questions about the Entity Manager before we move on to the second half of the lecture? The second half of the lecture, probably everyone in the class already knows, but what I wanted to do, because it's online, there's, the textbook, there's no textbook, et cetera, is I wanted the notes to be the study material, right? And so I want to have this in the notes just so you can look back on it, and I'm sure you might refer to this while you're doing it. What am I doing here? Oh, I'm over here. Okay. So let's talk about a refresher on 2D game math. And if you did any linear algebra or basic trigonometry, you know this stuff already, but I'm putting it in the context now of game programming, which may shine a little bit more light on it. So 2D games. Let's talk about a little bit about how, not the graphics work, but how the screen is laid out. So every game's graphics are drawn to a screen, right? Screens are a plane. They're two-dimensional. Screens are made of small, discrete elements that are called pixels. Pixels are usually, on your display, square things, okay? But if you look at, for example, the Atari 3200, I think it was 2600. The Atari 2600 has rectangular pixels. And so the pixels on the Atari are stretched when they're drawn to a 4x3 display because they're not actually square. But most modern implementations of games and monitors and operating systems and all displays, not all, but most displays have square pixels. And pixels have RGB elements inside them. So actual pixels, physical pixels. If you've ever gotten, whoever as a kid got really close up to the TV and looked, and you can see, like, you can actually see these red, green, and blue elements. Like, I did that all the time. I thought it was fascinating. I'm like, what's inside the television? There's all these lights. So, these pixels live in the display, and so every color that you see is actually a mix of red, green, and blue. And we talked about like the RGB color space before. So when we talk about 2D colors, in modern games, we specify the color of an object, whether that's a pixel or a shape, in a specific color space of the game or the display. So for example, we can talk about the RGB color space, so that's the red, green, blue color space. In our games for this course, we have the RGBA color space, so that's a red, green, and blue, and an alpha channel, which is transparency, and I showed that before. There's other color spaces called CMYK, so this is cyan, magenta, yellow, and black. And it's instead of B would be blue, so they put K for black. And this is used for a lot of printing. So printing and media and stuff is often done in this because the color space works out nicer for printed media. We could also have grayscale, so maybe colors from 0 to 256, which are just gray colors. And we could also have monochrome, so old displays that are either like a black pixel or a white pixel or a green pixel, depending on the monitor type. RGBA, when it comes to game programming, is by far the most common modern color space. And so each pixel gets assigned a color. And so in our game, essentially, every one of our objects is going to be living at one of these pixels, right? Well, apologies. Our objects can live at an arbitrary precision. And oftentimes, and actually in our course, our game world will be represented. Positions will be represented by floating points. But when things get drawn to the screen, they will be rounded to the nearest pixel for display purposes. But for the purpose of our mathematics and our collisions and stuff like that, we will actually be using floating point precision. So our system display is going to be this pixel grid. So that's why I've created it like this. Now, keep in mind that I'm displaying the mathematics here with 0, 0 in the bottom left, but SFML and most graphics libraries will have 0, 0 in the top left. Now, the mathematics of the additions, subtractions, multiplications, all that kind of stuff, it'll all be the same. It's just that I'm showing the math with this in the bottom left because it's just a little bit more intuitive for people who have done math courses like that. I'm going to move my camera down here so that it is not interfering with the slides going forward. Okay. So our system display is a pixel grid. The grid is in 2 dimensions, x and y, so we can use a Euclidean plane to visualize individual positions. Each integer position here is going to be a pixel on the display. And displays can be resized or full screen, so pixels could like appear larger. So what I mean by that is, for example, if we have set up our game resolution to be, say, 720p, so 1280 by 720, and then we full screen that application to a 1080p screen, then what the graphics library will do is it'll actually scale the elements up so that the pixels will look larger, okay? But what it's actually doing is just stretching some stuff out. Most APIs have 0, 0 in the top left. So again, importantly, even though our grid that we're showing these mathematics on is an integer grid, our objects in the game could live at an arbitrary precision, okay? So they could be floating point numbers. And all the mathematics works out exactly the same. It's just that in the slides, I want it to be integers so that the mathematics is a bit easier to show. But it still all works out if they're not integers. So let's look at an example here. Let's say that we have a position 2, 2, right? So this is our position, 4, 2. So again, 4 in the x direction, 2 in the y direction. What we can do is we can represent that 2D position as a vector. So we have a vector class now, and that's the vec2 class. And so the vec2 class is going to have elements x and y. So for this case, if we had a equal vec2, 4, 2, this is the vector from the origin to the position 4, 2. And we can think of a vec2 Someone said this is different from standard vector. Yes, but that I covered that in the last class. So our vec2 is different from standard vector. This vec2 is a data structure which holds an x component and a y component. So vec2 is different from standard vector. It's a mathematical vector, not a container vector. So thank you for bringing that up. It's good to reiterate that. And what the x and the y mean in vector terms is that this is the distance from the origin 0, 0 of the vector, okay? So it's 4 away in the x direction from the origin, and it's 2 away in the y direction from the origin. And we can see here that this vector points from 0, 0 to 4, 2. Let's take another point. Let's have another point B, and we'll create the vector from from the origin to B. So this one is 6 in the x direction and 7 in the y direction. So let's try some vector math, okay? So if we subtract b minus a, we get another vector c. So if b is 6, 7, let me use the laser pointer. If point B up here is at 6, 7, and a is at 4, 2, then the resulting subtraction of two vectors is their component-wise subtraction. So we take the 6, subtract the 4, we get 2. We take the 7, subtract the 2, we get 5. And so the resulting vector c is 2 in the x direction and 5 in the y direction. Now, this is important. So when we do vector subtraction, if we say destination minus origin, we get the distance. And in vector addition, if we have origin plus distance, we get destination. So what does that mean? Well, let's look at addition because it's a little bit easier. So if we take the origin, so let's say the origin here is the starting point, which is point A. And we add a distance, so let's say that distance is 2 in the x direction and 5 in the y direction. Then we add those two vectors and we get another vector, which is the destination. Okay? Similarly, if we want to get the distance between 2 points, we take the destination and we subtract the origin. If we go the other way around, then what we get is the reverse, okay? So if we took A and subtracted B, we would get a vector pointing from B to A, which would have negative values right here. So that's just very basic, like, you know, here are vectors and here's what adding and subtracting them means. Now let's go a little bit, and I'm not going to get too far into this. If you don't know this stuff, you really need to go back and review your math. So again, we have sine, cosine, and tan. We have the SOHCAHTOA, right? So we have an adjacent side, opposite side, hypotenuse. We're going to have an angle theta, and so this is all right triangle stuff, right? So you should know this. I just put that slide in there in case you don't want to have to Google some stuff if you forget exactly that cos is adjacent over hypotenuse or something. And yes, we're going to be doing math in this course. Oh my God, what a travesty. Now, if you weren't taught the unit circle, but or if you don't remember the unit circle, but you're taught this, then we'll just do a little bit of the unit circle, right? So we have a right triangle here. If we have a circle centered about the origin, the unit circle is the circle whose radius is of distance 1. If we have an angle which has this theta, right? So we have an angle of theta, which is between the x-axis and the radius here, then the point at which that vector touches the unit circle is at cos theta, sine theta. So cosine of theta is the x value, sine of theta is the y value. So opposite is y, right? So if you look at the SOHCAHTOA, then opposite is y, adjacent is x, the hypotenuse is r, so this would be the hypotenuse here. Sine theta is y over r, okay? And that's the y value here. Cosine theta equals x over r, which is the x value up here. Tan theta is y over x. All right. So we have these values out of the way. Now, again, I'm not teaching trigonometry. This is a refresher so that when you go in your assignment and you need to refer to this, you just have it in your slides. So here are examples where this applies to games, okay? If you have an angle and a distance, and you want to get the vector, how do you get that, right? So you can get that from here. So if we have an angle, theta, and we have a total distance that we want it to travel, what we want is the xy vector. And so we'll go into how to get that. Like we may want to do something like that, is what I'm saying, in a video game. So let's look at a speed, okay? So in assignment 2, we're going to be defining entity speed, so it might be the bullet speed, it might be the enemy speed, as s units per frame, okay? So we're going to have a speed s, and remember, speed is not velocity. Speed is going to be the total distance traveled per frame of the game. So over here, the speed is going to be equal to the hypotenuse of our right triangle. Maybe we have the entity which is going to be traveling at an angle of theta, right here. If we have a radius, so the radius of our circle, or the hypotenuse of the right triangle, is s. So we know that cosine of theta is x over r, sine theta is y over r. So we think about it in terms of the vector of the actual change in the x and y components, which is what we actually need in our game, then cos theta is the x change if the speed was equal to 1. And sine theta is the y change if the speed was equal to 1. So, to get the xy velocity vector, we have to multiply that by the speed value. So this is, if we're given an angle, right, and we're given a speed, we want to get the xy velocity vector that we're going to add to the position of an entity. So if we want to figure out the velocity from the speed and an angle, then our vec2 velocity is going to be equal to s times cos theta and s times sine theta. Okay? And the speed is the magnitude or the length of the velocity vector. So if later we called length on velocity, it would be equal to s, plus or minus the floating point rounding error. So again, that's the case where we have an angle and we have a distance or a speed, and we want to get the vector that we should actually be updating in the game. Okay, next example is if we have a vector and we want to get the angle and the distance, right? So if we have a vector, so if we have the hypotenuse, how do we get the distance and the angle? So let's say, for example, we have a player and we have an entity. So our player, let me just draw on this. Our player P would be down here. Our entity E would be up here. And we have some diff vector D, right? So let's say we want to get the distance from the player to the entity. So if we want the distance from the player to the entity, we're going to get this difference vector D. And remember, we subtract the destination from the origin. So distance from player to entity, we take entity and we subtract player. Now what we get is essentially, over here, we get x2 minus x1, y2 minus y1, right? So that's our vector D, is our distance vector from the entity to the player. Now, if we want to get the distance, the actual physical distance, rather than the difference vector, then that's just the square root of the sum of the squares, right? This is just Pythagoras. So that's how we get the distance. If we want to get the angle, then tan is equal to y over x, which is equal to d dot y divided by d dot x. Now, I'm not going to get into why this is, but if you actually want to do the reverse of this, so the arctan, then a theta is equal to atan 2f dy dx. So don't use atan for arctan in C++, use atan 2. Just do that. Atan won't give you the right angle. Okay. Now vector normalization. So if we have a vector, like let's say we have a vector from here up to here, then the length of the vector L is essentially the distance that it travels to get from the origin to the destination. So if we take the distance from the origin 0, 0 of this vector, so for example, if we have 0, 0 here, and we have like 3, 4 up here, then the distance from the origin of this vector is just the square root f of x squared plus y squared, right? And square root f is the floating point squared. So the length of our vector is just equal to Pythagoras with these. So if we want to normalize a vector, we take a vector and we're going to shrink it to length 1, but we maintain its angle. So to normalize a vector, you're essentially taking a vector and turning it into a unit vector, which is important for some cases. And normalizing a vector maintains its angle but changes its length to 1. So it makes it a unit vector. So the normal vector n, given a vector v, is going to be a new vec2. It's going to be the x component of the vector divided by the length and the y component of the vector divided by the length. And so where would this be useful? Okay, why do we want to care about vector normalization? Well, if we're talking about graphics, and especially 3D graphics, it's hugely important. And in some more advanced physics simulators, it's really important. But in our case, let's say, for example, that we wanted to shoot something, right? Maybe in assignment 2. So again, we're going to have the player at a specific location in the world, and that's going to be at a specific vector, right? At a vec2, px, py. And we also are going to have our mouse position. So in vector 2, we're going to click to shoot. And the whole point of this is that our bullet is going to have a specific speed. Let me just show the slide. So in assignment 2, our bullet shooting is going to move toward the mouse. In the config file, our bullet speed is defined as a scalar s. So what that means is that every frame, our bullet is going to be moving at a scalar speed s. But how do we get that speed vector, right? How do we take the speed s, given the player is at a particular location and we are shooting to a particular location, how do we actually get the frame-by-frame vector that we're going to be updating the bullet's position? So first, what we're going to do is we're going to get the distance vector d. So again, it's the destination minus the origin. So this is the mouse position x minus the player position x, and the mouse position y minus the player position y. Now, d is this vector, right? It's this whole vector right here. And that's going to be L. But we actually want that to be S, right? When we're talking about how much we want this to go every frame. So what do? We normalize it. So now by normalizing it, we make it of length 1, okay? So we're taking the vector that goes directly from the player to the bullet, and we're going to take that and shrink it so that it has speed or length S. So in order to take this vector and give it a length of S, we first normalize it so that it has a length of 1, and then we multiply it by S, okay? So that's just what we did before. So D has a length that we don't know yet. We figure it out and we normalize it. So now we have n equals d dot x over L and d dot y over L. So our normal vector now has length 1. And then our velocity vector, the vector that we actually update the position of the bullet, is going to be s times the normal vector's x and s times the y component of the normal vector. So see what we did there? We have a player position, and we have a mouse position, and we have a speed of the bullet. And so we want the bullet to travel in the direction from the player to the enemy at a given speed, and this is how we do it. Now, if we wanted this to be done, we can also do it another way, where we do it with angles, okay? So, instead of using vectors and the distance formula, we could do it with angles. So we have this d, right? So this d, this diff vector d, which we calculated, this also has an angle. And we could do it with angles if we want to, because that angle is theta. And so that theta is the a tan 2f of the y component and the x component. And make sure when you're passing into a tan 2, it's tricky, but the y component is first. Okay, that's very important. So if we recall the slide where we wanted a vector, and now we have an angle and a distance, or in this case, the distance is the speed, then our vec2 velocity is equal to s, which is the speed, times the cosine of the angle, and s times the sine of the angle. So if we have a player position and the mouse position, and we want to fire a bullet at a given speed, and we want to figure out the velocity each frame that it has to be updated, we can use either this or this. They both give the exact same thing. All right. The second thing that we have to do on assignment 2, and so the next lecture on Thursday, so Thursday assignment 1 is due, and I also give out assignment 2. Okay, so I know that there's no breaks from assignment in this course, but the reason for that is that I give you more time than you need, and that way people who are having a little trouble or people who may have more courses, you can submit anytime you want, right? You don't have to wait until the very end of the course or the very end of the due date in order to submit things. It's just that I want to give people as much time as possible to work on their assignments. So assignment 2 will be explained on Thursday's class, but something else that'll happen in assignment 2 is that every single entity in that game is given a circular collision opponent. So we've gone the physics route here and just assumed that everything is a perfect circle, right? And so the entity, therefore, will have 2 components in it which determine a collision. So whether or not a collision has occurred between, say, a bullet and an entity, or the player and an entity, or the player and an enemy, will be determined by 2 things. So we're going to have the position of the entity and the collision radius of the entity. Because if our entity here, so say for example we have the player and it's a circle, this radius is going to determine whether or not it's colliding with another entity. So how can we determine a collision? And I'm sure everyone out there could figure this out if they wanted to. I just want to give this to you in case, you're struggling a bit with the math. So here we have a case where we have one entity, which is down here at position x1, y1. And this entity has a collision radius of r1. Up here we have a second entity, which is at position x2, y2. And it has a radius of r2. So what we want to do is do the mathematics to see whether or not the 2 circles have collided. And here's a little bit of a spoiler for you, right? So the entities both have radiuses, and we can figure out the distance between the centers of the circle. So what we're going to do is we're going to determine if there's an overlap, which means there's a collision, by comparing their distance and something to do with their radiuses. So let's look at how we do that. So here again is that same diagram. So we have 2 circles. Circle 1 is defined by x1, y1, and r1, which is the radius. And circle 2 is defined by x2, y2, and r2. So we're going to get the distance between them, right? And you could just use Pythagoras for this if you want. But if we wanted to do it using the vectors that we've seen so far, we have the difference vector d, right? So we have the difference in the x and the difference in the y. That's just the component-wise subtraction. And that gives us this vector here. And now we want to take the length of that vector, which of course is Pythagoras. And then all we have to do is we have to realize the fact that if the distance between the 2 circles is less than the sum of their radiuses, then there's a collision. Really super simple. So again, this collision is a Boolean value, and if the distance is less than r1 plus r2, then there's a collision. That's it. Really, really simple for circles. Circles are by far the easiest things to detect collisions. But can we do better than this? Can we do better than what we just did? Okay, let me bring it up again. Can we do better than that? Spoiler alert, we can do better than that. Here is one of the first optimizations that you learn when you're programming games, okay? Square root is expensive. Now, square root has gotten far less expensive than it used to, okay? Square root essentially used to be a function that was called inside the math library, but now most modern processors have like a square root unit, and it returns like an approximation of the square root within some tolerance. It used to be super expensive. Now it's just kind of expensive. Square root is needed when we want to get the actual length of this vector, right? So to get length, we need square root. There's no way around that to get exact length. But do we need the actual distance? Do we need the exact distance? Well, let's look at the formula. What we're checking is if the square root of dx times dx plus dy plus times dy is less than r1 plus r2. How about we square both sides? If we square both sides, well, this becomes a variable which I'm going to call distance squared. Okay? So if we square the distance, we get distance squared. And now we can remove the square root. So if we take something that's a square root and we square it, we just remove the square root. So now this formula here, if we square the x's and add it to the square of the y's, we get the distance squared. And now what we have to do is square the other side, and we get the following. So if distance squared is less than the square of the sum of the radiuses, then we have a collision. And so now we have a formula which doesn't have a square root in it anymore. And in many cases, this is faster than using the square root. Okay? So we may have to do one extra addition or multiplication over here, but the difference, okay, is that we no longer have the square root. So the mathematical properties of all this are identical. We've just squared both sides, and we've replaced a square root with 2 or 3 operations, which is an addition and a multiplication. So a question in the chat was, doesn't this mean we're multiplying a lot of times than a few instances of square root? Yes, but multiply is far cheaper than square root. And so it's okay to do a couple of multiplies. And in actual fact, we can store the result of this as a variable and square it with itself so that we're only doing one addition, right? We can do little tiny optimizations, but you have to test that on a system by system basis. But for the most part, this line of code, implementing that will be much faster than this line of code. And it's identical in its comparison. So we don't calculate the actual distance because we don't need it in that case. So we can save the square root. Alrighty. The last thing we're going to need for our assignment 2 is how to generate random numbers in C++. Now, I know I'm eating my words here, but as I said, we're going to make a couple of exceptions in this course where it's necessary. I said that if there's a C way of doing things and there's a C++ way of doing things, use the C++ way. In this assignment, you can use the C way of generating random numbers. I'm not going to get into the security of random numbers because we're just generating where enemies spawn, okay? So the simplest way to generate random numbers in C++ is the rand function, which is also present in C. For serious security, this function is not considered secure or safe. But for this course, it's fine for our needs, okay? All right. Random number generators take a seed which determines the outcome of future RNG. And if you want to seed rand, you can use it with srand int. Why would you want to do that? Well, the default seed to rand in C is 0. So if it's not specified, your program will generate the same sequence of RNG every single time, okay? So if you run your program and you don't specify a seed, then every time you run your program, your enemies will be spawning in the exact same places, which you don't want. So what we could do, for example, and this is fine for the assignment if you want to do this, is you could take the time function. Time function returns the number of seconds since the beginning of the universe, which if you weren't aware is January 1st, 1970. And you say time null, this returns an integer, and then you can seed srand with that integer, okay? And so what this means is that you'll get a new seed every time you run this program for a new second. And so this is like a ghetto way of doing this, and it's completely unsafe, but the security of random numbers is not our like main point here, right? Okay. Now, again, I'm sure that you could all figure out how to generate random numbers within a range, but I just wanted to give you this slide so you can refer to it and make sure that your thing is proper. So for example, in our assignment, we are going to have a window, and you're going to be generating positions for the spawn points of enemies which are within the window bounds. So you want to generate an X value, which is within the window's width, and you want to generate a Y value, which is within the window's height. So how are we going to do that? So given a range of min-max, where this means inclusive, I'm just going to write a function. So let's say we have a diff, right? So the difference is going to essentially be the width of the range. So this is 1 plus max minus min. And what we are going to do in order to generate a random number, the rand function, when you call it, literally generates a random integer. So between, like, it's any of the integer values. So what's going to happen is we're going to take rand and we're going to use the modulus operator. And modulus operator, it's like the remainder operator, right? So if we have an array with, if we have 5 values, and let's say we take 7 mod 5, right? So you take 7 mod 5, you go 1, 2, 3, 4, 5, 6, 7, you get back to 2. So you're essentially dividing by that number and then taking the remainder. So if you want to get a random number between a minimum value and a maximum value, what you can do is take rand mod diff. And so diff is an integer, which is the width of the range. So r is now a random value from 0 to diff minus 1. Then all we have to do is add that r back to the min. And what happens there is we've gotten a random value between 0 and the width, and now we add it back to the minimum. So here's our function. Our random number that we want to generate between maximum and minimum, we just take min and add it to rand modulus 1 plus max minus min. And let's just look at an example of that. So there's our function. Let's say we want to generate a random number between 30 and 40. So we have the diff, which is 1 plus 40 minus 30. So there are 11 possible values. There's 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, 40. So there's 11 possible values. So we say r equals rand mod 11. So this gives us a value between 0 and 1 inclusive. And then we add this back to min, we get a number, which is 30, plus a random number inside this range of 0 to 10. And this also works if we want to generate a random number in a range of like itself, right? So if we have a range which is itself to itself, then 1 plus this, rand mod 1 always returns 0. And so we will just get the number back, okay? So that's how you just do the math for that. And that is basically all the mathematics and all the C++ and all the entity managing that we're going to need for assignment 2. So if I close this down for a sec and I go back to the website, then we just covered the entity manager and the math review. And so on Thursday, the entire lecture is going to be talking about assignment 2. So what has to be done, the config file, the marking scheme, and also what the bonuses are going to be for assignment 2. So for every assignment, assignment 2, assignment 3, assignment 4, I'm going to have bonuses. And so the bonuses are going to be able to get you bonus marks. But not only that, on subsequent lectures, I'm going to load up the coolest solutions and show the different bonus things. So for an example, on assignment 2, we're going to have a Geometry Wars clone as the game that we're making. And the right mouse button is going to be a special weapon. And so your job as a bonus is to make the coolest special weapon possible. And last year we had things like people spawning gravity wells and like People would like make bombs that shook the screen when they exploded. And like you can go crazy with the bonus stuff. Just make sure that you have the rest of the functionality done. So we'll be talking about the assignment on Thursday. Assignment 1 is due on Thursday. And I think it'll be a really fun assignment. And we're finally starting to get into the programming and the actual game programming. And then we're going to have a bunch of lectures before assignment 3, because assignment 3 is really where we start hitting home with like game programming, right? And assignment 3, by the end of that, you'll all be quitting school and making your own video games because you'll know so much, right? So that's it for today. I'll stick around for just a second if anyone has any questions. So would the range technically be 0 plus radius of spawned entity with minus radius of spawned entity? Yes. So what the question was for assignment 2, if I can pull this up. Oh no. Let's go to the blackboard. So if we have a window, right, and we have an enemy size like this, then the actual range that we want to spawn an enemy in is, oh geez, that's a circle, this is the range. We have to take the 0 plus the width of the enemy, or the diameter of the enemy, or sorry, the radius of the entity, and we have to take this width minus the width of the minus the radius of the entity, and the same thing with the height here, okay? Because one of the things that we're going to do on the assignment is that you can't spawn entities that are partially outside of the window bounds, and things are going to be bouncing around, and that's one of the, so that's why you need that modulus within a range. So you're going to be generating random values between this position and this position, and also between this position and this position. So yeah, it's not just the 0 and the width. There's that extra stipulation of the width of the entities. But we'll get into all that for assignment 2. Cool. So there's no more questions. I'm going to stop the lecture there and see you all on Thursday.